Frances Arnold to take the lectern. It's up there.
So 3D printing of the nose, you'll all have your own choice of nose in the near future. So pretty big challenges face us, providing food, fuel, energy, water, and health and well-being to this planet's population without destroying the other members of the planet, the biological world. All right, let's see if I can. There we go. And in fact, it's the other residents of the planet to whom I look for inspiration and for solutions, because I think that human engineers have a great deal to learn from biology. When you think about it, remarkable for efficiency and elegance of the solutions it has to its own challenges. Think about it. Living systems obtain energy and resources from the environment, convert that into self-replicating, self-reproducing machines. Living systems adapt, they evolve with time. And 4 billion years of Darwinian exploration, innovation, trial and error, success and failure has led to a spectacular array of solutions to the problem of being alive, which are constructed from equally spectacular molecular machines that do this work of transforming energy and matter into other forms. My prediction, along with many others, is that we will use some of nature's solutions to solve our problems. We heard about that this morning, synthetic biology from Craig Venter. And we'll also have to create new ones. And you heard some about that from Angie Belcher, who's doing some remarkable work in creating new biological entities. The short 60 years, though, that's been since the discovery of DNA's double helical structure has seen an incredible revolution in the technology. Now, we have not yet synthesized life from scratch. That has not yet happened, but we're getting wonderfully close to doing it. And we can synthesize an entire genome. That's what we heard about this morning. Put it back into a cell, and a cell will read it as its own. The problem is, and this is where Craig Venter left off, is that we know how to synthesize DNA, but we don't know how to compose it. The products of evolution it's like a Beethoven symphony. It's elegant, it's intricate, it's tremendously complex. And we don't know how to write music like this. All we do right now is grab bits and pieces from the environment, cobble them together in some new thing, and they're not necessarily well designed for what we want to do. Remember, organisms do a very good job at making other organisms, but we don't know how to compose the DNA for taking carbon dioxide and sunlight and turning that into gasoline. That's a highly non-natural function, and it's something we have not yet figured out how to do. And we certainly don't know what is the code for a longer, healthier life, as much as we would like to do that. So to compose new DNA, I look to the algorithm by which all this came about in the first place. We've been modifying the biological world for a very long time. This is not a new capability. But in the past, breeders had to rely on sexual recombination, where monkeys go with monkeys, and corn goes with corn, and you can't really mix the two together. So this is what we've been doing for a very long time, but with the technology that's now available, remember, we can synthesize anything. In the test tube, we can recombine monkeys and worms and you name it. And so here's the real challenge, is that to compose new life, we take this new capability of modifying DNA in the test tube. And it's a big power, right? It's both a blessing and a curse, this power that we have, because we don't know the rules for breeding now at the molecular level. These are the challenges that the engineer faces, is we have this capability, we know we can design new biological entities, but we don't know whether it should be sex with 3 or 33. We don't know what level of mutations to dial into the process. And what can I create? What can I expect to make? A good breeder can anticipate what the progeny might look like and choose features that come out of that. We don't have this kind of experience in the laboratory, and that's the fun part, of course, that's the research. But I'll tell you, and I'll remind you, that no other engineering discipline has the ability, with a reliable algorithmic process, to take a bad design and turn it into a good one. That's the power of evolution, that's the power of artificial selection, and we should be able to use that. So in the last few minutes, let me just share with you a few examples on how we can improve on biology's designs for the benefit of humans, and particularly for health. Engineers, for quite a while, have recognized that the code for synthesizing important pharmaceutical, biologically active molecules like this one, Taxol, very important anti-cancer therapeutic, is encoded in the DNA of the organism that makes them. But very often, we don't have sufficient supply of these compounds, and they're far too complicated to synthesize in the laboratory. So why not take the DNA that encodes these things and transfer that into microorganisms, where that DNA can be optimized, the appropriate control sequences can be added, and you can then produce these compounds in large-scale fermentations for very low prices. And this is an extremely active and proficient area of research where products are being made and sold and commercialized now. The machines that do the work of converting cheap things like sugar into Taxol are proteins like this, the enzymes, that really are truly amazing little engineering marvels. For example, this one, I know that many of you are not deeply into the chemistry as I'm in, but if you knew what this enzyme could do, it would knock your socks off. This enzyme can take oxygen from the air and insert it into a carbon-hydrogen bond. Think methane to methanol, one of the biggest problems. This enzyme can do that. Not only does it do it, it does it at room temperature pressure and in water. It does chemistry that we have not figured out how to do, but it learned how to take iron, an abundant metal, and activate it in such a way that the enzyme can hold a substrate in place and insert that oxygen. You have a bunch of these in your bodies, and with tools like these evolutionary design processes, where we can overcome our near complete ignorance of how the DNA does encode this function, we can create new versions in the laboratory that will mimic all of the capabilities of your human enzymes, so that you can, for example, synthesize rapidly the metabolites of drugs and test them for toxicity. And what's even more exciting is that we can go on beyond where nature never wanted to go. Instead of just mimicking what nature's done, we can create versions of these enzymes that do whole new chemistries. And I won't go into the details because I don't have the time, but this is such an exciting area of chemistry research and chemical engineering research, where we can now incorporate into cells the vast repertoire of chemistries that synthetic organic chemists have learned over the last couple hundred years and encode them directly inside of cells so that the cells can be our factories for the future. Of course, proteins and biological entities do a lot more in healthcare than just make things. They are the therapeutics themselves. Think of the monoclonal antibodies or the enzymes that can be used to treat diseases. Those can be modified and improved in the laboratory through reliable engineering evolutionary processes. The future is wonderful. It's full of possibilities. When you think about how many things nature has already invented, for example, these amazing pore molecules that take light and respond to that by opening up a membrane, selectively allowing materials to pass through, the ultimate separation technology. Well, engineers have started to incorporate these, expressing them inside of neurons so that you can control the brain with light. Engineers have started to use viruses. I love Angie's work because she uses the virus to make a battery. Here's an example where engineers use viruses to deliver genetic material to difficult places like the photoreceptors of a retina. And when the viruses evolved in the laboratory, you can reach many more parts of the eye than what a virus would naturally do. It becomes working, it works for us now. So I'll close just by reminding you, this really is the era of synthetic biology. And I have to hope that we will use it to solve real problems. It's a powerful technology, and that the life that we are going to write will be beautiful, and that it will enrich our own. Thank you.
Thank you very much, Frances. I'd now like to invite Dr. Jeanne to this podium.